Okay, so last time we showed that this sequence is exact. So degree 0 to degree 0 class group to integers via the degree, which means that all degrees are possible, all integers are possible, and this surprisingly we got from the zeta function definition, which was not required to define the sequence, but to prove its exactness. Interestingly, zeta function was needed. And then we showed that it is z is equal to this L function divided by something very simple, 1 minus t times 1 minus qt. So degree of L is 2g, that's the numerator, degree of denominator is 2. So this is the rational function. L function has important properties. L of 0 is 1 and L of 1 gives you the size of the class group. So H of C we had defined yes, H of C was this definition, size of the degree 0 class group. That's called the class number of the curve. Why is this number finite? The way we had defined class group, it seemed to be infinite.
We showed CLD and CL0 are same and then counted CLD.
Yeah, so actually that needed a proof. We showed that, yeah, we showed on the first slide, we showed that the degree 0 class group is actually finite. Yes, it's actually the number of non-equivalent, non-negative divisors.
CLD has a non-negative divisor, right? Or a divisor can be.
No, so we showed this by, I mean, it's a non-trivial argument. We reduced it to a non-negative divisor, and then we used the definition of this LD sheaf to show that we can now assume the divisor is positive.
Can you repeat it once again?
This proof. So this proof was via, I mean, once you find something in LD is greater than or equal to 1, once you find something in LD, then that function f, you can add it to your D and it becomes positive. So ultimately it actually is you only have to count these non-equivalent, non-negative divisors of degree D. That we showed is finite. Yeah, so that's an interesting proof. It goes via degree positive, but it tells you something about degree 0 also. Okay. Yes, this argument was for D greater than or equal to G. It was only for large D's. For large degree you argue, and then that gives you information about degree 0 class group. Okay. So yeah, after that we have shown this connection of zeta function with counting points. So zt is equal to exponential of the generating function. And from that we get this nice formula. We get this formula in green that counting points on the curve which are in the finite field q raised to m, that is basically given by the number of points on the projective line plus some error, and the error term is also given very exactly by the complex roots of L function, which at this point is totally black box. We don't know how these alpha i's behave, but we do know by the functional equation symmetry that you can pair up the complex roots so that the product is q, right? So we reach till this point. Now the magical thing that
Oh, you use that one, right? Z of 1 by qt is that relation we use.
the functional, use L of 1 over qt. So actually it is not, alpha is not the root, it's the inverse root. We are looking at LT as product of 1 minus alpha I t. So when you substitute 1 over qt, alpha I over q will be equal to some other 1 over alpha j.
Q over alpha is equal to alpha.
Yeah, it's the same thing. Yeah, so alpha I over q will be equal to some other. So by that you get that the product is equal to q. Yeah, I mean this is a bit inverted. So you will get 1 minus alpha I t will become 1 minus alpha I by qt. So t also goes in the denominator.
Q by alpha is like, because you're inverting the root. Z of 1 by qt, right?
Yeah, so t is replaced by 1 over qt. So
Oh, by qt. Or alpha I t by qt.
so this is the problem. It's t is also in the denominator, so you have to normalize by t and then see what is happening. So alpha I by q will be a root, which means that alpha by I by q will be equal to some 1 over alpha j. So that's the sequence of transformations. Yeah, so that means that alpha I wait, there is still something wrong. No, it's okay. No, it's actually when you transform, you have to see that t. You have to look at this as t minus alpha I by q. So alpha I by q will be equal to 1 over alpha j. That's the pairing. So functional equation gives you this symmetry. Okay, so the next thing we will prove is the Riemann hypothesis, which conjectures that the norms of alpha i's are equal, which means that they have to be square root q. So Riemann hypothesis conjectures a strong symmetry namely that all these alpha I norms are equal. Yes, so it's not clear why you would want to conjecture that. It seems outrageous that all the norms of alpha, all these complex roots, they have equal norm. But once you conjecture this, then you know what they should be, then they should be equal to square root q from the previous property. Because the product has to be q, if they are equal, then the norm has to be square root q. Yeah, so this is what the Riemann hypothesis is. This jump to strong symmetry is obviously inspired by Riemann's original hypothesis, where he jumped from functional symmetry to strong symmetry on the zeros, saying that all the zeros, they lie on the line half, real part equal to half. So that is the half which is also appearing here. So this half is the same, gives the same kind of picture. Okay, so yeah, so what this comes from is you have to look at the zeta s version. So in that zeta version, what it is saying is that the zeros of zeta are on the line real part equal to half. Okay, just like the original RH. Which is still an open question. So the original Riemann hypothesis is still unproved, but that also boils down to such a statement that all the zeros of the zeta function lie on real s equal to half. So that's what is actually true over finite fields, curves over finite fields. And in terms of counting, what this is saying is that the number of zeros of the curve in the finite field fq raised to n, this is equal to the norm of sigma alpha I to the n, I going from 1 to 2g, which now will be upper bounded by 2g q raised to n by 2. Okay, so this is the, you get this nice bound on the number of points. So if you think of genus as small and q as big, then you deduce that number of points on the curve in fq is almost as much as q plus 1, right? Which is a completely mysterious out of scope statement, because it's a general curve over a general finite field, and we don't know currently how many points there are even just in the base field fq. But this will basically mean that the points are q plus 1 plus minus error, which we can assume is quite small because it's square root of the main term.
So that you put z of q minus the second statement.
Mm-hmm.
All the zeros on the line real of s is half, but we showed that the square the mod of s is 1 by square like q like half, right?
No, no, this was alpha I was the inverse root.
That's okay. Especially that's a complex number. We just showed that its norm is half.
Yes.
We haven't shown that the real part of that is half.
No, so S is equal to A plus IB. Q raised to A is the I mean, we have shown that no, it should follow from here. It should follow, right? Because it's happening in the exponent. It's Q raised to S. So you get information. So Q raised to S gives you the the Q raised to real S gives you the magnitude. Yeah, or maybe one more thing, some simple observation indeed needs to be made, but let me skip that part. We just proceed with our current Riemann hypothesis. So this means that number of FQ points on C and when we say curve we obviously mean smooth projective. Right, so on a curve FQ points they are in the range q plus 1 plus minus 2g square root q. So this is the simple elegant expression we get. It's as much as the line with error of square root and genus. So this is the fundamental result we want to show. So we'll prove this by doing a sequence of reductions and finally using the LD sheaf. Okay, so the LD sheaf result is use is very mysterious, but the reductions which we will do will be more intuitive. So let's start with the reductions. So the first reduction is again to do with base change. So RH is true for ZTC if and only if it is true for Cn. So you can pick any n, and if you can show this, let's say you go to FQ square, look at the curve as FQ square curve, and there if you prove Riemann hypothesis, then it's true also for FQ. Okay, so we want to go higher up. The advantage higher up is that you may get to a very big field, finite field, but a very big field, and then some things may be easier to prove. So let's first show this reduction. So we know from the older identity that zeta function of the curve divides t raised to n Cn. Okay, we had shown this earlier. In fact, there was this strong identity in base change that we had shown. We had shown this identity that z t raised to n comma Cn factorizes using the base zeta function, substituting for t eta t, where eta is an nth root of unity. So we had this factorization proved. So let's remember that. So in particular, zt comma c is one factor of this. In fact, why not write this? So this we know, hence zt comma c is a factor. Take eta equal to 1. So which means that if you have Riemann hypothesis for the right hand side, then you have it also for the left hand side. Because so Riemann hypothesis for zt comma Cn, right? So you will have information for once you have information for the roots of t comma Cn, actually this has to be, let's do this carefully. So if you have a root beta t or a factor beta t of zt comma Cn, then 1 minus beta eta t is a factor of z t raised to n Cn. Right? In fact, this is if and only if. So we have this property that if beta is an inverse root of zt comma Cn, then beta eta is an inverse root of zt raised to n comma Cn, where eta is obviously arbitrary nth root of unity. Beta raised to 1 by n, yes, that's right. Correct. So that is not good.
raised to power n, right? Because this Riemann hypothesis.
Oh, yeah, that's the trick. Yeah, you're right. Okay. Yeah, that's a good point. Okay, so thus Riemann hypothesis for Cn would imply that beta raised to 1 by n, sorry, beta first, beta is equal to q raised to n by 2, which will mean that beta to the 1 by n is equal to square root q. Which implies that all roots of zt comma cn, t comma c, satisfy this, which implies Riemann hypothesis for the original curve, right? Because every 1 minus alpha t that divides for curve C also divides the RHS, and we have that information. So we have information for C just by the division. Conversely, what we have to show is assume Riemann hypothesis for zt comma c. So yeah, what happens then?
To use that only 1 minus beta t and 1 minus beta eta given earlier.
Yeah, so so this means that so 1 minus alpha t let's just look at, yeah, this is slightly different. You have to look at, you have to utilize this z, yeah, eta t comma c.
All roots are from alpha eta raised to k, where alpha comes from zeta t c.
Yeah, let's write that down. So as 1 minus alpha t dividing zt comma c, this implies that 1 minus alpha eta t divides eta t comma c we can deduce that zt comma for zt comma cn well, first of all, this will divide T n C n, and then what does it tell you about Z T comma C n?
Alpha raised to 1 by n has to be
These are the only factors. Yeah, so since these are the only factors, you
And 1 by alpha eta t raised to n, that form will be helpful. 1 by alpha eta t raised to n divides that, then we can break them down.
no, but we only know. Yeah, okay, we can take product over eta. This we can do because we had actually a product of z eta t comma c. Yeah, so this product actually divides z t n comma c n, which is, I guess,
1 alpha raised to power n t raised to n.
yeah, right? It's 1 minus alpha n t raised to n. So alpha n t divides t c n, which means that the inverse root norm is n-fold. So that's q raised to n by 2. Yeah, I thought it's trivial, but actually it requires some calculations. So we have shown both sides. Okay. So that is one reduction. What happens when you do base change? Riemann hypothesis should be true in an equivalent way. Second proposition is now about another kind of reduction. So the following are equivalent. So Riemann hypothesis for zt comma c, which is the statement that inverse roots norm is square root q. Second statement will be for the counting estimate instead of the root of L function, the counting. So as long as nd minus q to the d plus 1 is less than equal to a plus b times q raised to d by 2, for some constants a, b, n, and all multiples d of n. Okay, so this is a bit complicated to read, but just the inequality is what you should focus on first. So as long as the count for q raised to d sized finite field points is somewhat q raised to d by 2 with flexibility given by these constants a and b, for all the multiples of n, where n is also some number which is constant. So say n is 10. So as long as you can prove this for let's say multiples of 10, d is multiples of 10, that also is enough. Okay, it's so you can jump over the d's. You don't need to show this for all d, but as long as you show it for a constant fraction of d's, that will also imply the Riemann hypothesis. So this is a relatively non-trivial equivalence. This has to be compared obviously with what we said before, which is this line at the bottom. We said here that it's less than equal to 2g times q raised to n by 2. But then it's true for all small n's. Now if we are saying that even if it is true for just constant fraction of the small n's, it's good enough. Okay, so that's a significant weakening. Let me define what a constant is here actually. So constant means independent of I guess q and d, or just I think independent of d. So A, B, capital N they have to be independent of D because we want to change D. That's what constant means. Right. Okay. Yeah. So let's prove this. So 1 to 2 we have already seen. For all D. So the converse is the interesting part. Yeah, how do we get norm of alpha exactly square root q from this approximate information? So replace the base field by q to the n. This big N which is a constant, and now let us only look at extensions of this q raised to n. So from this q raised to n we go to q raised to d because d is a multiple of n. Q raised to n is contained in q raised to d as we vary d. So that is the setting. So the hypothesis implies that this formula that we have this is the strong property that actually nd minus q raised to d plus 1, the error term, we have an exact formula. So let's use that formula. So sigma alpha I to the d norm is less than equal to a plus b q raised to d by 2. For all d divisible by n. That's exactly the hypothesis. From here we have to deduce that alpha I norm is square root q. It doesn't look very easy because alpha is a random complex number, so it could have been anything. I mean, alpha i's can all be 0, so this inequality doesn't seem that strong. So let's use the L function from where alpha is come. So what is the product of alpha is? So product of alpha i's can be use the symmetry. So we can pair up the roots in a such a way that each product is Q. This is by symmetry. Or by functional equation symmetry. So the product is actually Q raised to G. This is a strong information available. So alphas are not arbitrary. Their product is actually Q raised to G, which means that if we show that each of them the norm is less than equal to square root Q, then we'll be done. Right, because if all the norms are less than equal to square root Q, and the product you want to be Q raised of these 2G things you want to be Q raised to G, then all the norms have to be equal. Not a single norm can be strictly less than square root Q. So we just have to show this upper bound actually, that alpha I norm is less than equal to square root Q. So recall that the L function factors as, so alpha I are the inverse roots. Okay, so let's take a log of this. So that will be equal to okay. So we are taking minus log both sides. So minus log gives you log 1 over LT, and this RHS it gives you basically you sum up over minus log of 1 minus alpha IT, which is just sigma alpha IT raised to D divided by D. Negative sign cancels. And then we rearrange, so we get this expression. So in fact, we could do this. That's the expression we get. So sigma alpha I to the D is sitting there in the coefficient of T raised to D by D. Yes, so something I need to change here. There is a typo happening. So let's continue to call this as FQ. Just to simplify the notation, so not only have I changed the base, but this q raised to n I continue to call it FQ instead of introducing a new variable. So now when I say q raised to d, what it is actually is originally it's q raised to nd. Okay, so just
The proposition of this Q raised to n, right?
yeah. Okay, so okay, if it's problematic, then let's not do that. Let's call it q prime. No. So q is in the input, given in the input. Q prime is q raised to n. N is the given constant. So fq prime to the d is actually q to the nd. And now check that hypothesis 2 indeed is giving me q raised to d by 2, right? And product of alpha I is indeed it's indeed q raised to g. Yeah, I think this is q prime is the correct choice. Okay. Yeah, let's see whether it will work. So here I want to plug in the estimate now. So what is that? The estimate is a plus b times q raised to d by 2. Right, so I can now take norm both sides. The RHS I can now estimate the coefficient that norm is a plus b q raised to d by 2 and norm of t raised to d, which I can rewrite as the a part. So a part is what? It's sigma t raised to d by d, which becomes log of and the b part. Is that correct? So a times essentially minus log of 1 minus t and b times minus log of 1 minus t root q. Yeah, that's right. Right, so I expanded minus log and then I have again written in closed form. So which means that the RHS converges for any complex t if the norm of t is less than square root q raised to minus half. So as long as you take t to be less than 1 over square root q, you can see that both these summands they will converge, and so log of 1 over LT will converge. This is just done to rule out the poles of L function, right? So this means that the poles they are outside this range.
T can't be 1 also, no? It has to be greater than
Oh no, 1 over square root of q.
that is log of 1 by 1 minus T also that term, right?
No, this expression, this is already a fraction, right?
1 over.
Yeah. Q is minimum 2, so it's less than 1 over square root 2. Correct. So that's important. So from this what we learn is that in fact we learn about zeros of L. So zeros of LT are greater than equal to this, right? Because if they were in norm, because if the norm of zeros of LT was less than 1 over square root q, then you can pick that as t. LT vanishes, so LHS becomes divergent, right? So we have learnt about the zeros of LT, which means that we have learnt about alpha inverse.
One second, can you repeat that 1 second? If it's greater than 1 by square root q, then
Oh, the
zeros of T.
no, LHS converges when t is small.
Yeah.
So if LHS is diverging, then it means t is big.
No, but it's only if that, but it could converge for more values also. No, it should FN only here.
No, the zeros of L, when LT is 0,
Yeah.
then LHS is
Okay.
that diverges, right? It's 1 over 0 is infinity. So log of, it will become log of infinity. Yeah. So this is now telling you about alpha I inverse. So that is greater than equal to 1 over square root q, which means that alpha I is less than equal to square root q, which implies that for all I 1 to 2g, the norm is exactly square root q. Okay, so this finishes the proof. That's the Riemann hypothesis for ZTC. Okay, so that's a very interesting reduction of Riemann hypothesis. Yeah, so actually FQ prime I did not need. It gets inbuilt. Yeah, it gets inbuilt because D is a multiple of big N all the time. So no, I think I need to change this. This is not, there is a problem. So D is greater than or equal to 1.
These alpha is come from FQ.
Yeah, no, alpha i's are fixed. They are coming from ZTC. Yeah, that is not that's not the problem. I think the problem is that this sum is going over all D's. Uh, but the estimate I have is only for multiples of n. So how do I handle that?
And we can go that last base change to this f q to the power n.
Yeah, q prime, that's q prime.
We can change that, right? I think base ZTC to ZTC. There's new base field
Mm-hmm.
above, and I think we can prove it there, and it will imply first part also.
Yeah. So what should I change in this? Somewhere I have to
This
change.
alpha has to come from, I think, this new field, like new Z.
Oh,
So that will change the base. Basically.
I see. So then I have to change everywhere but to q prime. This will be q prime to the g. Yes. Where alpha I are roots of they come from L T comma C begin. Which I think we are calling LT now. So for this LT, when I sum up, now I can go over all these, right? And when yeah, so I go over all these, and this Q has to be Q prime. This is Q prime.
How is that hypothesis to implement that?
Yeah, that's easy. So the hypothesis is for see there the D is multiple of n, so you can think of Q prime raised to arbitrary D prime. D prime all integers, all natural numbers, and Q replace Q by Q prime.
But those alpha is now come from a bigger.
Yeah. So alpha. No. This was only a statement about count. There is no alpha here.
No, these hypotheses to be took summation alpha a to d to show that is less than a plus b q raised to d by 2.
Mm-hmm.
So those alpha come from the bigger curve.
Yes, but when you change the base, alpha I will become alpha I to the n.
Okay.
So it will become alpha I to the n multiplied by d prime. So yeah, that part is actually implicit, and then for those you will have q raised to ng. So I think so we are using this fact that in base change, alpha I becomes alpha I to the n, which we showed in the previous proof. So this has to be put here. Well, if you want, we can change alpha I to alpha I prime to avoid confusion. So alpha I prime is actually alpha I to the n. Yeah, let's do it properly. Right, so now I can use it. So sigma alpha I prime to the d is less than equal to a plus b q prime to the d by 2, simply because it's multiple of n is now embedded there. Yeah, this was a typo which needs this kind of notation actually. So okay, what did we learn from here? So this means that which means that RH for ZTC holds. Okay. Yeah, so actually we are using the first reduction. So we first prove it for changed base, and then from there we go to the original curve C. Yeah, that's great. So now you see why we actually need multiples of n. If you miss a multiple, then this argument may get into trouble. Because what we are really doing is, first we are doing a base change to q raised to n. So all multiples of n, we should have an estimate. And then it's actually equivalent. Okay. So the next reduction that we need is to make the cover so every smooth projective curve we have seen is, it can be seen as a cover of the projective line. But this is not the best cover, because what is happening at the level of fields? At the level of field, you have this k x1, x2 and the curve, say given by some equation. Contains kx1. So there is an arrow from curve to the line, and there is an arrow from the function field kx1 to the function field of the curve, right? It's opposite arrow, which is basically, the arrow is simply containment in the bigger field. The problem is that this field extension that we are looking at, this may not be Galois. So it is a finite algebraic extension, but it will be better if we make it Galois. So we make it Galois, and then we study Riemann hypothesis only for that.
What's the difference between Galois extension and algebraic extension?
Yes, so in Galois extension, all the roots will be present. If you think of x1 as fixed, all the x2 should be available. So right now what is happening is that for an x1 only one x2 may be available. So I will see this in more detail by an example. So we want to make it Galois. That's the one word reduction. That is, we want this Kc, we want Kc to have all roots for x2. Okay, so function field, this extension may not have all the roots x2. We want to give it all the roots. Sorry?
X2 or capital F?
Yeah, when I say roots x2 for f.
Oh, it's not a splitting field basically.
Yeah. So see, we cannot talk about both the variables together, because I mean here the transcendence degree is 1, so we can't say I want all x1 because x1 are infinitely many. x1 takes values from k bar. So I don't want to talk about x1. Let us just think of x1 as something fixed, which is properly we are going over the function field kx1. That's the projective line function field. We are going above it. So above it now there are only few x2s. Out of those few x2s right now we have only one. I want all of them. So I have to go to a bigger extension. And that is called a Galois cover of the line. Okay, so we want Kc to have all roots of f with respect to x2 and thinking of x1 as fixed. So that is the rough intuition. X1 is fixed in the projective line and I want all the x2s for a fixed x1. So that's the move to the Galois cover.
It's something like we have an fq and all the roots and fq of x and fq to the power n of x. All the roots and somewhere there of this capital F.
Say it again.
We have an fqx.
Yes.
Now we want to go something fq to the power n of x, something like that. So that is
Fq to the power.
and some higher field or k.
No. So it's yeah. Let's do this for an example. So let's see an example first. So let C be this elliptic curve. x2 cube minus x2 minus x1 square equal to 0 over the base field k fq. Okay, so I mean it's just the affine patch. To make it smooth projective, you have to introduce x0. But for x0 equal to 1, this is the affine patch. X0 equal to 0 will give you the point at infinity. So this is an elliptic curve. It's basically x1 square equal to x2 cube minus x2. So what is the problem in the function field of this? So function field is called big K. It will be this field So this is a finite extension, is a degree 3 extension of kx1, which is basically the function field of the line. Okay, so over the line, this is degree 3 field extension. The problem is that once you fix x1, you get, this gives you only, once you fix x1, it becomes a univariate in x2 of degree 3. For example, x2 cube minus x2 minus 1. So there should be 3 roots. Now, since you have modded out by just this polynomial, so it gives you only 1 root. Other 2 roots are missing.
How do we not know that the roots are in kx1 and x2 like that?
Oh, because when you randomly fix x1, x2 cube minus x2 minus say 1 is an irreducible polynomial. So since it's irreducible and the roots are distinct, they're all conjugates. So when you add 1 root, you don't expect the other 2 to appear.
I'm saying like x2 is a root. How do we not know like x2 plus?
No. So look at x square plus x plus 1. So when you mod out by that, in that case you will get both the roots. But then let us look at x cube plus x plus 1. So when you mod out by this, you go to an extension where you get 1 root, but the other 2 roots you don't get. So actually you have to add a second root, that will be degree 3 times degree 2, so degree 6 extension. Then you get the splitting field. So here also in general you have to go to a degree 6 extension, because the symmetric group of on 3 elements acts S3. So you have to go to degree 6, and this is only degree 3. So how do you go? So basically we want to go above this. Which may not be a splitting field over kx1. Okay, so over kx1 you want to go to a splitting field, that's the goal. So if you go to a splitting field, then you get the Galois cover. So we correct this by moving to the splitting field of so splitting field K prime of x2 cube minus x2 minus x1 square over kx1. So suppress x1 as a constant, and then it's a univariate of degree 3, and generally its splitting field will be actually degree 3 times 2, so degree 6. So K prime over kx1 is 3 times 2. Yeah, so that splitting field is what? This is now again a transcendence degree 1 field over small k. So by our general theory, we have written the theory in a general form. So this is again a curve, right? Because our curves, smooth projective curves, are always actually just translates degree 1 fields. There is it's in one-to-one correspondence. So we can again talk about a curve. Let's call it C prime. So C prime is a Galois cover of C and of the projective line. So that would be the next reduction, which is of a more fundamental type. It's more geometric. So K prime contains K, contains Kx1, which contains K, which is equal to Fq, and this is degree 6, or this was degree 3, and this is degree 2. Because yeah, you already have one root, so the remaining part is only quadratic. You attach another root and you get all 3 roots. So that would be the price to pay. And K prime over K is Galois. That is, they are yeah, I don't want to. No, I think I should not make this statement. It's not Kx1, but is K prime over K Galois extension? Not really, right?
Like splits F, right? That's what
It just splits, yes, but it splits only single polynomial.
can't
So
split all then.
problem is, yeah, the problem is that square root of x1 may not be present.
It can't split all then, so it will be algebraically close.
Yes, correct.
Galois extension of F, I mean that will be the precise statement.
Yes, I think it's the Galois extension of f.
The function field we're using. Like
The function that we are using here, which is yeah, if we call this f x1 x2, yeah, so this is not, I think the problem is it's no, so for Galois extension, don't you need this property that if a polynomial has a root, then it should have all the roots?
I think it's a normal extension.
Yeah, but so a normal and a separable extension is called Galois. So will that property be true? I think this has to be checked. If it has one root, then it should have all roots. I think, okay, then I can go back. I can say, for now, I can claim that both are Galois. That is, they are separable and normal. Yeah, so these are the extra properties. It's not very important for our Riemann hypothesis proof, but for the proof we only needed this k prime which splits single polynomial f. But I think you can reduce these Galois extension properties also. Yeah, so coming back to the curve, we have now a new curve. Be the curve defined by k prime as it's a transcendence degree 1 field over small k. So this also defines a curve that's the curve C prime. And this C prime arrow C arrow P1 is called the Galois cover of C. Yeah, so what it is doing, so I'll discuss this again on Friday, but what it is doing is that on the projective line, if you took a point which is fixing x1, then you get 3 x2s, 3 points in C. So there are 3 points in C which map to the same point on the line. They are opening up more. So now when you go to C prime has 2 points which are mapping to the same point in C. So these, yeah, so yeah, no, not exactly. So we are not in algebraic closure, so we are in k equal to fq. So actually when you fix x2, there is a corresponding point in C. We don't know how many, maybe only 1 point is there. And now that 1 point will open up to 3. So 3 are mapping to 1 and 1 is mapping to 1. This is the generic picture.
But I can also point 1 mapping to 2 and those 2 also 3.
Yeah, but those are exceptions. So we will show that they are very small in number. So the generic situation is 3 mapping to 1 mapping to 1. So since we were getting only 1 point in C, we had to go to a bigger curve, and that's the Galois curve. There we will get all 3. Usually, for usual x2s or x1s, we will get 3. Yeah, so we'll come back to this point next.